In our last video, we were looking at sequences, which we generally wrote like this, A sub n or B sub n. And we said you could have a finite sequence or an infinite sequence, although for the purposes of this class, we'll generally have infinite ones. We talked about monotone sequences and bounded sequences. We said ultimately our goal was to be able to look at a sequence and determine if it converges or diverges. And as far as properties of sequences, we went over a few of them, like the boundedness and whether it's monotone or not. And again, I stress, if you'd like more of a review of it, we mentioned arithmetic and geometric sequences that you may have seen before. If you'd like more of a review of that, let me know, and I'll get some of my other videos from my trig class, and I'll post them in our Blackboard page too, just for review. But we want to kind of expand on this a little bit in this video. And math people kind of look at something a certain way, meaning, suppose I have the sequence A sub n, and it's 1 plus 3 plus 5 plus 7 and so on, all the odd numbers. I wrote pluses there. I don't know why. It's a sequence. So it's 1, 3, 5, 7, and so on. But then, well, to be honest, from a math perspective, once we have a bunch of numbers like that, our almost natural reaction is to say, what can I do with those numbers? And one of the things we can do with the numbers is to add them together. And we get what's called an infinite series. So we have sequences of numbers. Now we want to look at series of numbers. These kind of go hand in hand. And in this case, I could just have that series right there. 1 plus 3 plus 5 plus 7 and so on. You've all seen this summation notation, obviously, from when we did our Riemann sums. And then, well, now that I have this series here, I want to know what the sum is. And admittedly, in this case, this one is pretty obvious. It's infinity. And frankly, from a math perspective, it doesn't really tell me much. I mean, I'm adding up a whole bunch of numbers and they go off to infinity. I mean, not that big of a deal. But the question becomes, well, maybe if I have something like this. We'll do it this way. 1/2, 1/4, 1/8, and so on. That's another sequence. Clearly, I start with a half and just multiply it by 1/2 each time. You should actually probably recognize that as a geometric sequence with a common ratio of a half. And if I try to write it over here as a series, let's see, n equals 1 to infinity, 1 over 2 to the n. We all understand how this indexing works. When n is equal to 1, I get 1 over 2. When n equals 2, I get 1 over 2 squared, 4. Okay, good. That's it right there. And I'm adding up an infinite number of numbers. So do I get infinity? I get infinity here. If I add up these numbers, do they add up to infinity? And we kind of end up in this bizarre situation where we say, well, if I add up an infinite number of things, do I get infinity? Maybe here I'm adding up things, but they're really, really small. I mean, really small fractions. Maybe adding up an infinite number of fractions won't give me infinity. Maybe it'll give me something else. I don't really know. And that's actually what we're going to spend a lot of time in this chapter looking at. And again, we'll see, as I mentioned in the last video, we'll see why later on. But essentially, we want to look at a bunch of series and be able to say, if I look at that infinite series, do all the numbers add up to 100, or do they add up to something that isn't? Not 100. Do they add up to infinity, or do they add up to something that's not infinity? And if an infinite number of things add up to something that's not infinity, what does that tell me? It doesn't even tell me anything. Does it mean anything? And that's what we want to look at. In order to do that, we need some notation and terminology. First off, if I have some series, A sub n, if I want to know what that series adds up to, there are different ways to try to figure it out. And I will actually point out, as we will see as we go throughout this chapter, when we talk about sequences, we say, does a sequence converge or diverge? And if it converges, what does it converge to? We'll use essentially the same terminology here. If I have a series, if it adds up to a number that isn't infinity, we'll say it converges. If it doesn't, we'll say it diverges. And sometimes we'll be able to figure out what that sum is. Other times we won't, which means we'll just essentially say, does it converge, yes or no? And if the answer is yes, then a lot of times I'll just stop there. And there'll actually be reasons for that we'll see later on. But for right now, I kind of start with, how do I determine if it converges? And there's different algebraic math ways to do this. One of them is to look at what's called partial sums. And I will point out, as a student myself, when I learned this, there were certain things that, for whatever reason, just confuse you as a student. Partial sums were one of them. I was good with sequences. I liked sequences and all that. Partial sums, for whatever reason, my brain just did not compute very well. But the idea is, suppose I have this series right here, which I understand is a sub 1 plus a sub 2 plus a sub 3, all the way out to sub a sub n, and then it continues going on forever. A partial sum, maybe I say s sub 1, that is the sum of the first term, which is just one term, a sub 1. S sub 2 is the sum of the first two terms, a sub 1 plus a sub 2. S sub 3 would be a sub 1 plus a sub 2 plus a sub 3. And so on. I can have S sub n, which will be the sum of the first n terms. And I can keep on going. But now, these are numbers right here. Like, if I knew what the terms of the series were, I could find a sub 1, obviously. I could add the first two terms and get s sub 2. I could add the first three terms and get s sub 3, and so on. Which means these partial sums actually create a sequence for me, S sub n. This is called the sequence of partial sums. And now I can really say, if the sequence of partial sums approaches a number, a limit, maybe s, because that's s sub n, if the sequence of partial sums approaches some number s, then that series converges, and it converges to s. And again, as a student, my brain just really kind of stopped understanding what was going on there when we were doing this. But maybe if we use this, and we're not going to be able to fully expound on this because we don't have enough yet, but the series we just had. Well, if I wanted s sub 1, that would be a half. S sub 2 would be a half plus a fourth, which is 3/4. S sub 3 would be a half plus a fourth plus an eighth, which would be 7/8. 4 plus 2 plus 1. And we'll do one more. S sub 4 is a half plus a fourth plus an eighth plus a 16th. 8 plus 4 is 12, plus 2 is 14, plus 1, 15. It's 15 over 16. And clearly, the terms of this sequence of partial sums is getting bigger, a half, 3/4, 7/8, 15, 16ths. But it also looks like it's really just closing in on something. Will it ever get bigger than 1? We'll see later on, actually later in this lecture, that it won't. The next term, s sub 5, should be 31 over 32, I do believe. And now, if I just look at this sequence of partial sums, it looks like S sub n is approaching 1. And then if these partial sums are approaching 1, then this sum up here should approach 1 as well. And that would tell me my series converges and it converges to 1. There's a lot of math involved there, and we'll actually see some of it later in this chapter once we've expanded on this idea a little bit. But for right now, all I really need to know is, if I look at a sequence of partial sums, and that sequence of partial sums approaches a number, then the original infinite series converges. But maybe to flesh that out a little bit more, we're going to look at a few specific examples and see what we get. Meaning, I mentioned the geometric sequence before. We all know from trig and whatever, a geometric sequence is a sequence that differs by a common ratio, multiplied by r. There's a formula for it and all of that. But if there's a geometric sequence, we can also have a geometric series. When we write the geometric sequence, it's generally the first term times the ratio to the n minus 1. I think that's the standard way of writing it. Which means, if I write my geometric series, the first term would be the first term listed here. When n is 1, I get r to the 0 and I just get a. Plus AR, when I multiply by R, plus AR squared, plus AR cubed, all the way up to AR to the n minus 1, because the power of R is always 1 less than the term. If this is the nth term, it's the n minus first power, which means then I can write my series right there. And there's a nice form for the geometric series. And now the question is, does the geometric series converge? And I will point out again, this is one of the things that you may have seen, and again, if you take my class, you do see this in trig. So hopefully you remember it. If not, I'll go through this really briefly. But the idea is, well, if I want to know if that converges, look at the sequence of partial sums and see if that converges. So, S sub 1 would just be A. S sub 2 would be A plus AR. And now I'm just going to jump to S sub n would be A plus AR squared plus AR to the n minus 1. Now I'm just going to look at this term. This term right here. And I'm going to multiply the whole thing by r. So if I do that, I get r s sub n equals AR plus AR squared plus AR cubed plus AR to the n minus 1 plus AR to the n. And keep in mind, there's an n minus second term here, which when it gets multiplied by r becomes the r to the n minus first term. And then this last term, when it gets multiplied by r, becomes r to the n. But now, these are not entirely straight because I was kneeling while I wrote it. But now, I'm going to subtract these two things. Here, s sub n minus r s sub n, if I factor out the s sub n, I'm left with 1 minus r. 1 s sub n minus r s sub n, factor out the s sub n, you know, with 1 minus r. Here, if I subtract, I have an a, there's no a down here, so that's going to stick around. But now, AR minus AR cancels, AR squared minus AR squared cancels. Clearly the next term here will be AR cubed, which will cancel there. AR to the n minus 1 will get canceled by that. But then there's no AR to the n term down here, so that's going to stick around. And keep in mind, we're doing top minus bottom. So all that's left is A minus AR to the n. Now, if I just look at that, I get S sub n times 1 minus r equals, factor out the a on the right, 1 minus r to the n. Now, since I care about the nth term, the sum of this series right here, of the sequence of partial sums, solve for S sub n, I get a times 1 minus r to the n over 1 minus r. And from trig, you should probably recognize this is the formula for the sum of a geometric series. But I care about the infinite geometric series, which really just means this n is going to go off to infinity. And the question becomes, when does this converge if n goes to infinity? The only n in this whole sum right here is right here. It's the power of r. If r is bigger than 1 or smaller than -1, raising it to a power makes it get bigger. And then this will blow up to some weird number. But if the absolute value of r is less than 1, meaning r is between -1 and 1, a fraction less than 1, absolute value, then raising it to a power makes it get smaller. And as n approaches infinity, as I look at the infinite series, that fraction approaches 0. Raise a fraction to a really high power, it approaches 0. Which means, as n approaches infinity, if the absolute value of r is less than 1, that term goes to 0. And then I get S sub n, and actually maybe here I'll say S sub infinity, just so we're clear. The infinite sum is equal to a times 1 minus 0, so just 1, so all that's left is a, over 1 minus r. And now that's the sum of an infinite geometric series, as long as the absolute value of r is less than 1. If it's not, then this doesn't work. So now I know, if I have a geometric series, I can quickly determine if it converges or diverges by just looking at the value of my r and then plugging it in here. So, good to go through a few examples. Maybe we'll do the geometric one we mentioned before. So we had a sub n was equal to 1 over 2 to the n, which was 1/2 plus 1/4 plus 1/8 and so on. And doing our little trick that we did before, we said that it looked like it was equal to 1, based on the few partial sums we wrote out. Now we can check that here. S sub infinity, the sum of that geometric series, the ratio is clearly 1/2. That's less than 1. So it should be the first term, which is 1/2, all over 1 minus the ratio, which is 1/2. And I get 1/2 over 1 minus 1/2, which is 1/2, which is 1. And now I know the sum of this series right here is 1. It's convergent. You get closer and closer and closer and closer to 1, and ultimately it adds to 1. Kind of. We'll see that later on. But now it means we can expand on this, and for the sake of argument, suppose I have the series n equals 1 to infinity of 2 times 3/5 to the n minus 1. Does that series converge or diverge? If you cannot tell by looking at it what type of series it is, one trick you can do, and I will stress this throughout the chapter, I do it myself sometimes, list out the first few terms. When n is 1, n minus 1 is 1 minus 1 is 0, anything to the 0 is 1, so I get 2. Plus the next term, when n is 1, I get 2 times 3/5 plus 2 times 3/5 squared, and clearly that's geometric with a ratio of 3/5. 3/5 is less than 1, ratio has an absolute value less than 1, that one will converge. If I want to know what it converges to, formula, it's the first term all over 1 minus the ratio. And I would point out, I know you all have calculators. Don't do this in a calculator. It'll actually mess you up. It's easier to do by hand. That's 1 minus 3/5. 1 is 5/5. 5/5 minus 3/5 is 2/5. You know the rules for fractions. The 5 comes up top. 5 times 2 is 10. It's 10 halves, which is 5. Nice and simple and easy. There is another trick we get out of this. And I will point out, this is the trick. You can see a variation on it, an algebraic type variation on this, going all the way back to middle school, because I tutor middle schoolers, and I've actually seen them use a different variation on this trick. But I actually prefer the geometric one, just because I think it's cooler, because I teach calc too. But suppose I have 0.14 repeating. Let's see. I think the rule is irrational numbers are non-repeating, non-terminating decimals. That's a repeating decimal, which means it's not irrational, which means it has to be irrational because it's a real number, which means it's a rational, R-A-T, not irrational, I-R-R-A-T, a rational number, which means it can be written as a fraction. Write that as a fraction. And I will point out again, there's an algebraic way to do this, which is pretty cool. But now you can impress your friends and show them the Calc 2 way to do this. And the idea is, what does 0.14 repeating mean? Well, that means 0.14, 14, 14, and so on. But another way to write this is 0.14 plus 0.0014 plus 0.000014, etc. And clearly that pattern will repeat as the 14s repeat. But then, how do I get from here to here? Shift my decimal point 2 places, I multiply by 1/100th. How do I get from here to here? I multiply by 1/100th squared, which is from here to here it's 1/100th. I'm thinking from the beginning. But from here to here, I shift 2 more places, it's 1/100th. And now clearly, this number, which is this repeating decimal, can be represented by this geometric series. The ratio, 1/100th, clearly less than 1, so clearly this series converges. What's it equal to? The first term, write them as fractions, 14 over 100, over 1 minus the ratio, 1/100th. Then I get 14 over 100. That's 100 over 100 minus 1 over 100. That's 99 over 100. The two 100s cancel. And I get 14 over 99. And there's the decimal representation of that repeating fraction. There's the fractional representation of that repeating decimal. So again, I really like these geometric series and these little tricks that we can kind of use for other math we've seen before. I just think they're really cool. But anyway, moving on. A couple other series I want to look at. Suppose we have this. 1 over n minus 1 over n plus 1. Again, as I said, there are different ways to think about these. That's clearly not geometric, subtracting 2 fractions. There's different tricks I can try, but for right now, one thing we said we could always do is list out the first few terms. If n is 1, I get 1 over 1, which is 1, minus 1 over n plus 1, which is 2. The next term, when n is 2, I get 1/2 minus 1/3. The next term is 1/3 minus 1/4. all the way out to 1 over n minus 1 over n plus 1. And then it would keep going. But now, if we look at this, if I kind of rearrange my parentheses, 1 minus a half plus a half, that's just 0. Minus a third plus a third, that's just 0. Minus a fourth, there would be plus a fourth here. The previous term here would be 1 over n, that's a 1 over n. And really, ultimately, S sub n, the nth partial sum, will just be the first term minus the last term. Similar to my geometric approach. But then, if I care about finding the limit of this sequence of partial sums as n approaches infinity, well, as n approaches infinity, 1 over n plus 1 approaches 0. So as n approaches infinity, S sub n approaches 1. And it converges. I always kind of like this. Essentially, I start at 1, and then I just subtract off less and less and less, subtract and add less and less and less, and I just approach where I actually started. I kind of come back to it with this alternating adding and subtracting trick. My brain likes how that works out. But a lot of these series, like arithmetic and geometric, get names. A series that looks like this is called telescoping. Essentially, I want to assume, without knowing officially why they named it this way, it's this nice simple little thing that telescopes out to this big huge thing, but then collapses back to itself when you solve it. And I think that's the idea. So apparently telescoping series converge. And again, I would point out, just like with the geometrics and all that, if you're unsure what type of series you have, just plug in the first few terms and see if you can find a pattern to work with. Next, suppose I have the series 1 over n, which is 1 plus a half plus a third plus a fourth, and so on. This gets a name. This is a really special one. It's called the harmonic series. And I'm kind of stuck with the question, does that converge? I know that geometric series, like the one we did, 1 over 2 to the n, converged because essentially they were fractions and the fractions got small enough fast enough that they didn't really matter and it converged. Here I'm adding up a bunch of fractions. Do these fractions get small enough fast enough in order for this to converge? And I'm deliberately using the wording that I am to harken back to something we have done before, which I'm not going to mention here, but I'm hoping this will trigger memories in your head. And actually, in the next video we'll go back to what we did before. I'm just hoping to maybe let you think about that first. But, as it turns out, I don't really know. And yes, I will point out, I actually do know if this converges or diverges. But essentially, based on what we know now, it's not geometric, it's not telescoping, there's no subtraction or anything. I don't actually know if that converges or diverges. And the idea here is essentially the same as it was with integration. I learn a trick, U substitution. Then I find an integral that I can't solve with U substitution, so I come up with another trick, integration by parts. Then I come up with an integral that I can't solve, and I have to find another trick, trigonometric integration or something. Same idea here. I now know how to tell if I have a geometric series and if it converges. I know how to tell if it's telescoping and it converges. This is neither of those things. Does it converge? We're going to have to think about that a little bit. We're actually not going to get a good answer today. But we do get some theorems that are important. If the infinite series is convergent, then the limit as n approaches infinity of a sub n equals 0. And notation as well as the direction of this theorem is really important. We're not going to prove it, we just need to really understand it. This is a series, this is the sequence from the terms of the series. And understand what we're comparing here. The sum of the series and the limit of the terms of the sequence that give me that series. If the series is convergent, then the limit of the terms of the sequence has to be 0. And just to go back to the one we know, 1 over 2 to the n, a half, plus a fourth, plus an eighth, and so on. That series was convergent, then the limit of the a sub n's is 0. But sure, my sequence a sub n was just 1 over 2 to the n, which clearly approaches 0. But keep in mind here, and this is important as far as, for those of you who've done logic before, and I know it pops up a lot in math, this is a conditional statement, if this, then this. The converse of this, which means you flip the order. So if the limit of the a sub n's equals 0, then the series is convergent. That is not true. Just because the limit of the sequence is 0 does not guarantee that your series is convergent. And that's like fundamentally important here. This theorem, this statement only works in this direction. If my series is convergent, then the limit of the sequence has to be 0. Which, if you think about it, makes sense. If I'm going to keep on adding things together, and they're going to approach a number and not shoot off to infinity, then the things I add on have to get smaller and smaller and smaller. Because if they don't, then I'm going to shoot off to infinity, because I'm adding big numbers, for lack of a better way of saying it. I have to keep adding smaller and smaller and smaller numbers so that I don't shoot to infinity, which is exactly what this is saying. But again, the limit of the sequence being 0 does not guarantee that the series is convergent. But this gives rise to our first test. The test for divergence. If the limit as n approaches infinity of a sub n is unequal to 0, then the series diverges. This is actually the contrapositive. If you've done symbolic logic before, when you have a conditional statement, you have the converse, the inverse, and the contrapositive. The converse, where you flip the order, this, then this, is not equivalent to the original conditional statement, but the conditional statement and the contrapositive, where you flip the order, this first, then that, and negate them, equals 0, not equals 0, convergent, divergent, that's called the contrapositive. And mathematically and symbolic logically, you can actually show those are equivalent. Which means, since this is true, this is true. If the limit of the sequence is unequal to 0, then the series diverges. And I would point out, this is the first test, the test for divergence that we're going to learn. We're going to learn a lot of tests. And fundamentally important to these tests is the same thing going all the way back to, say, mean value theorems and things like that, first derivative tests from Calc 1. The statement is important and the conclusion is important. Before you needed, say, your function was defined on a closed bounded interval, things like that. Same idea here. This is incredibly important. If this, then this. But this says nothing about convergence. It's a test for divergence, which means the only conclusion you can get from this test is divergence. If you get convergence from this test, you're doing it wrong, because the test can't tell you convergence, it can only tell you divergence. That will be true of all of the tests that we do. There will be conditions like this, and then there will be conclusions, and not a lot of times, but quite often, you'll do a test, and the conclusion you get will be, I don't know. And then you'll just have to try a different test until you get the test that works. So here, suppose I have the series 2n plus 4 over 3n minus 5. And now, given the length of this video, we're going to shortcut this a little bit, but, well, this test for divergence says I can look at the sequence. But if I look at this sequence right here, I can go all the way back to my basic definitions of limits from Calc 1, and I know as n approaches infinity, this approaches 2n over 3n, but then the n's cancel, and it approaches 2/3. If you will, if you're thinking about this as a function, rational function, has a horizontal asymptote at 2/3, going all the way back to pre-calc. But the limit of this sequence is 2/3, which means the limit is unequal to 0. Conclusion, divergent. That series diverges. And again, if you think about it, what this is saying is, as n gets bigger, the terms in this series, the terms in this sequence for each n approach 2/3, which then means ultimately I'm really just adding 2/3 plus 2/3 plus 2/3 plus 2/3 an infinite number of times. And if I add 2/3 infinitely, I get 2/3 times infinity, which is infinity, which is why it's going to diverge. But suppose we have the harmonic series. If I have that series there, if I look at the sequence a sub n equal to 1 over n, the limit of this is 0. So what's the conclusion? I don't know. Because here, the limit of the sequence is 0, so this test simply doesn't work. It only works if the limit is not 0. As soon as I get 0, I do not say the limit is 0, so it doesn't diverge, it converges. That just tells me this test works for this series, it fails for that series. And I have to come up with another test. And in our next video, I think we'll look at a couple more tests and actually find a test that will let me determine if that harmonic series converges or diverges. Because as of right now, it's kind of up in the air. I do stress, again, right here at the end, because I can't stress this enough, in the same way that you learned rules for derivatives, then you learned rules for integration, this entire chapter is going to be rules for tests of convergence or divergence. And all of them have important statements like this and important conclusions. And ultimately, on every problem that you solve, if you're trying to determine convergence or divergence, we'll do other things, but if you're determining convergence or divergence, you need to mathematically show convergence or divergence, which means I want the statement of the test, see if this series converges. Nth term test for divergence. The limit of the a sub n's is 2/3. Show the math, like I did here, not much. Conclusion, series diverges. You need to show the math step by step correct. If you try to do it here, you say, inconclusive, whatever, more work, and you try a different test. We're going to have a lot of tests, 8, 10 of them, something like that. You need to know every test, all of their statements, and all of their conclusions, and make sure you write them out correctly, because if you don't, you won't get credit for anything. One of the major points here is your ability to write out the math formally and correctly apply all of the tests. So I will be looking for that. Like I said, we'll look at some more tests in the next video. If you have any other questions, I want to see more examples worked out as we go, just let me know and I will do that as I make these videos.